Let's say you were just tasked with setting up a base station for the first time, and you needed to provide an NTRIP RTK corrector service to your boat. You get your Pelican case with the base station, some SOPs on how to set up the Trimble radio, and that's about it. If you're anything like me, you probably wish you had some kind of broad understanding of all of these concepts before you get elbow deep in that base station. So how about you get yourself a cup of coffee, kick your feet up, and spend the next 5 minutes of your life with me, learning about base stations, RTK, and NTRIP. A base station is really just a GPS receiver that sits in one place completely motionless, collecting GPS data that you can use to correct other moving GPS receivers or rovers, like the PAWS MV systems we have in our boats. That GPS data gives you the position of the phase center of the antenna, which is really the thing you need to keep motionless. Lots of times you see them mounted on tripods to ensure that they're in a fixed point. If that tripod gets attacked by a bear or falls off a cliff, your position is going to be a bit off. So what about benchmarks? I thought base stations had to be set up on top of benchmarks. I mean, heck, I've seen antennas mounted on some piece of metal sticking out of a roof. What's up with that? Well, the key is whether or not you really want to establish a long-term station. In other words, if you need to revisit or reoccupy the position, you should have a permanent benchmark to mark and hold that physical position. For our temporary stations, I don't really care about some long-term occupation. I just need a stable antenna to measure the errors in real time so I can correct my rover position. So what do I mean when I say you're using base station data to correct other receivers? Well, one technique GPS receivers use to get a position is through code-based pseudo-ranging, or the process of estimating distances based on the time it takes a known code modulated on the GPS L-band carrier signal to go from satellite to receiver. If you get two GPS receivers, a base station, and a rover close enough to see the same satellites, you can log data on both through the same time period and calculate their differences in position. With each receiver seeing the same satellite, you can also determine the errors in your measurements and cancel them out through a process we call differential GPS. Along with code-based pseudo-ranging, the fancy receivers we use also measure the phase of the carrier. To understand this carrier code thing, let's consider FM radio. Turn on the radio and tune to 94.7, and you get a carrier frequency of 94.7 million cycles a second. If someone in the studio hits the A string on a guitar, it's going to be carried or modulated on that carrier wave to the tune of 440 Hertz, or 440 cycles a second. For GPS, the PRN code signal is carried on the L1 frequency carrier. Since the carrier oscillates much faster than the code, we can make very precise ranging estimates relative to a cycle. The problem is that all of the cycles look the same. It's a bit like having a tape measure that has centimeter marks, but all the meter numbers have been erased, so I don't know if my measurement is 10.26 meters, or 11.26 meters, or 15.26 meters. For GPS, how do you know how many cycles occur between satellite and receiver? Well, getting an exact integer count of how many cycles is enough of a problem that it has its own name: integer ambiguity resolution. The answer to this problem is math, something called double differencing, and, as with most things GPS, more satellites is more better. Double differencing is pretty simple in concept. If you take two receivers and two satellites, and you look at the integer ambiguity change over time, your mathy approach should be able to tell you a fixed integer number of carrier cycles from receivers to satellites. After that, you just look at where you are in the phase within that last cycle, and bam, you get a super accurate range and position. So I still haven't mentioned RTK, or real-time kinematics. Kinematic is basically just carrier phase GPS in fancy tech language. If you do these carrier phase measurements and get those corrections to the rover in real time, you got RTK. It is that simple. You might also hear people talk about float and fixed RTK. Well, it all comes down to how close you get to resolving an exact integer number of cycles between satellites and receiver. If you get an exact count, you got fixed RTK. If you get a floating point number, it is float RTK. Pretty straightforward? Okay, so we should probably talk about NTRIP for a bit. NTRIP stands for the Network Transport of RTCM via Internet Protocol. Basically, it's a fancy way of saying I'm getting GPS stuff in RTCM messages and sending it over the internet to some other place. To get NTRIP working, you need an NTRIP server, an NTRIP caster, and an NTRIP client. The server is the base station receiver, providing the correctors. The caster is a computer you set up that takes in all the data from the base stations you have and forwards that data on to the client. The client is the computer you have set up on your boat that gets the data from the caster and sends it as a corrector to your POS. There isn't anything really special about the client. You just need some free NTRIP software and the login for the caster computer, and away you go. Thanks for watching, and good luck out there.